Hello, good evening, friends, and welcome to my YouTube channel. And welcome to all my subscribers as well. And those who are new to my channel, they all are welcome. And as you all know, that I do post videos related to different topics. So, continuing the series, today I'm posting a video. This is my fourth video of continuing the series of electronic devices and circuits. So, let me share my screen with you. Whatever the content that I will share with you is mm, um, particularly from the book of the Robert L. Boylston, but majorly from this particular book, Boylston, and uh, and some of the topics I will be covering through the internet as well, and some of the topics I will be sharing my insight with my knowledge and my understanding. So let's continue the topic with this fourth video of the series of electronic devices and circuit. You can watch other videos in the previous sections, which are mentioned in the playlist electronic devices and circuits. So let's discuss today the resistance level. Basically, when we talk about the resistance to the diode, there are two types of characteristics of the resistance which are measured. One is the AC resistance or is the DC resistance. AC resistance is generally dynamic in nature, whereas the DC resistance is uh, static in nature. So let's first study the this. Let me change the pointer. This is the mouse pointer is fine. The DC or the static resistance. DC or the static resistance means when the DC current is applied to the diode, then it will behave as a the characteristics will behave in a manner that it will have a resistance that will be denoted by voltage across the diode over the current through the diode. This is the DC resistance. So I already told you in the beginning, there are two types of characteristics. One is AC resistance or the static resistance. One is DC resistance or the, sorry, AC or the dynamic resistance. The other is the DC or the static resistance. So initially we are continuing with the DC or the static resistance. So now, as you can see, there is a initially the current is zero. As soon as it achieves the knee voltage, the current increases, and this is VD and this is ID. And the resistance VD over ID is known as the DC resistance of a diode at a particular point. So you can easily understood, like suppose if you want to have a resistance at this point, you will take the voltage at this point, this is the voltage, then the current at this corresponding, the VD over ID will be the static DC, static resistance. So the typical value, the DC resistance of a diode will range from 10 ohm to 80 ohm. So if you understood what is the general or the typical value of the DC resistance or the static resistance of the diode is 10 ohm to 80 ohm. You can note it down from here. I'm just highlighting it also. So let me highlight. This is the, yeah, let me change the color of the highlight pen. Uh, Let me change the color to orange. Yeah. Okay. So this is done. Now, 10 ohm to 8 ohm, this is highlighted. Now, again, continue the next topic. The next topic. Mm, So this is a question on this. You can easily solve this question if you have the PDF of this particular book. Then you talk about the dynamic resistance. The dynamic resistance, the DC resistance of a diode is independent of the shape of the characteristics in the region around the point of interest. Whereas a DC, AC or the dynamic resistance, AC resistance is known as the dynamic resistance. It depends. Let me check the proper volume is coming or not. Hello, hello. Yeah, proper volume is coming. So let me just share my screen. The screen is already shared. Yeah, sorry for this particular glitch. Now let me close this. Yeah, Hmm. Now, what is the DC or the dynamic resistance? Sorry, AC or the dynamic resistance. So when the AC current is applied, then we talk about the AC resistance. So you can see that you can get the formula. The AC resistance is denoted by RD is equals to the change in voltage across the diode, whereas the over the change in current over the uh, change in current through the diode. Delta denotes the change. See the difference. The static resistance is the actual voltage at that point of time, whereas the dynamic resistance is the change in voltage at that particular point of time. So change in voltage over the change in current is known as the dynamic resistance or the AC resistance. Now you can see this point. Let me highlight this bit for you. Yeah. In general, therefore, the lower the Q point of the operation, smaller current or lower voltage, the higher is the AC resistance. If the Q point means operating point. Those who have studied the transistor, uh, the AC analysis of any particular device, there is a point known as Q point. Q point means the point at which corresponding value of the current and the corresponding value of the voltage. When these two corresponding value are meet at a point, that particular point is known as the operating point or the Q point. So in general, therefore, the lower the Q point of operation, smaller current or the smaller, the higher is the AC. If the Q point is small, if the Q point is lower, then the higher is the AC resistance. This is the general prediction mm, about the dynamic resistance or the AC resistance. Now continue. You can solve this particular problem by your own. Let move on to another topic. So this is the solution of this problem. Now, average AC resistance, you can simply understood the average AC is delta VD over delta ID from point to point. So if you move from one point to another, you can have the average AC resistance. So these are the typical values. DC, DC, RD, DC or static resistance is equals to RD is equal to delta VD over ID, where the AC is equals to delta VD over ID is a 26 millivolt over ID. And the average is equals to delta VD over ID. So these are the three different structures by which you can understand the AC resistance, DC resistance, AC resistance, and the average AC value. You can predict from these particular graphs. Now, there is another topic that is quite important. That is a diode equivalent circuit. See, I told you the symbol of the diode initially in this particular video and video before this. So you can check out that particular instant. Diode has a particular equivalent circuit. But I told you in the beginning, in the previous video, that there are two types of condition. One is the ideal condition of the diode, and other is the uh, so let me just there is some I'm just checking the layout. Layout is see. Let me stop the recording for a second. So I'm sorry for this particular glitch. Yeah, I'm resuming the recording, and let me share the entire screen. Yeah, now it's visible. Now let me, it is looking like this, but I'm just getting this new feature of the layout. Layout will be kind of this. Yeah, this is fine. This kind of a layout will be there. So I told you, yeah. So thanks for supporting me, and let's in the next section it will not happen. So it was the problem with the layout. Uh, yeah. So the screen is shared. Now, as you can see, I told you in the beginning, there is a particular symbol of the diode, and symbol is of two types. One is the ideal diode, and other is the practical diode. Practical diode have some resistance, have some capacitance also, and have some cut-in voltage. Whereas the ideal diode have zero cut-in voltage, there is zero capacitance, and there is no resistance related to that. So according to the practical condition, there are two types of diode. One is the ideal diode, and other is a practical diode. So the ideal diode, you understood, it will act as a on switch or the off switch. Whereas the practical diode will have certain resistance, certain capacitance, or certain cut-in voltage. There are three factors which will affect the operation of the practical diode. So the practical diode will have a condition known as piecewise linear equivalent circuit. It will piecewise means it will have three steps: cut-in voltage, capacitance, and the resistance. The capacitance, resistance, and the cut-in voltage will be denoted the piecewise linear equivalent circuit, and that we will see in this feature. So you can see this particular graph. There is a voltage, there is a current. The initially the voltage is zero. Initially, as the voltage is increasing, the current is zero, and as soon as the cut-in voltage is achieved, zero point 0.7 is achieved, the current is increasing linearly. It is increasing by a certain rate, which is almost linear. Initially, it is increasing at a fast rate, then it becomes linear, then it got saturated. It is not showing in the saturation is not shown over here, but it does sometimes it does get saturated. So these are the condition which is with the uh, piecewise linear diode. And as you can see in the equation, in the graph, like there are three conditions are shown over here. One is the symbol of the diode is shown. As you can see, the symbol of the diode. Let me put the charger. The battery is about to drain. So it's perfect now. So you just see over here. See this condition. This is the plus and this is the minus. This is the diode. The forward current is denoted by ID. The voltage is denoted by VD. And you can see this zero point 0.7 is the cut-in voltage. 10 ohm is the average resistance of the diode. And this is the ideal diode. So ideal diode will not have these two components, whereas the practical diode will have the cut-in voltage and the resistance. And I told you the capacitance also. But at present, the capacitance is not considered over here. It will be considered when we will study the capacitive effect of the diode. So for now, you just have to consider the cut-in voltage and the average resistance and the ideal diode. So these is known as the components of the piecewise. These are known as the components. Let me highlight this. These are known as the components of the piecewise linear equivalent circuit. So you understood there are two conditions. One is the ideal diode and other is the practical diode. However, the ideal diode and practical diode are both are same. Both are not same, but there is a difference that in ideal diode there is no cut-in voltage and no average resistance. But in case of the practical diode, as you can see in the diagram, there is a cut-in voltage and the average resistance is connected, is associated with that. So continue the further. Now this is the simplified equivalent circuit. I told you the piecewise equivalent circuit. Now look at the simplified equivalent circuit. There is just a cut-in voltage 0.7. The voltage is increasing, VD is increasing. You can see in this blue line. And as soon as the cut-in voltage is achieved, the current goes straight away. So at the 0.7, the current increases rapidly with a straight line. So this is a simplified version of the diode, simplified symbol of the diode without the average resistance. But it doesn't exist practically. It is a simplified. And what is ideal? I told you in the beginning, there are two types of diode, ideal diode and a practical diode. Look at the characteristics of the ideal diode. See, in reverse bias, there is no current. So it is zero. Voltage is zero and the current is zero. But in case of the forward characteristic, as soon as the voltage is increased, the current straight away increases at the 0 point. So you can see this blue line. This blue line is increasing at the zero voltage only. So as the voltage increases, straight away increases. So this condition is the on switch, this condition is the on switch, and this condition is the off switch. And now you can see the symbol of the diode. It does not have any cut-in voltage, and it does not have the average resistance as well. So therefore, there are three conditions that we can see. One is the piecewise diode, other is a simplified model of the diode, and third is the ideal diode, ideal equivalent circuit of the diode. But actually, there are two scenarios, ideal and practical. But in practical sense, there are three scenarios, piecewise, simplified, and the ideal. But generally, there are two, practical and ideal. But ideal diode does not exist in reality. It is a hypothetical model. Or we try to achieve the ideality in terms of the diode. Now, you got the point what I'm trying to say, as you are a student of electronics. So you can see this particular diagram, a summary table over here. This is the piecewise, this is simplified, and this is the ideal. You can take a screenshot over there and continue the discussion. Now, I will talk about the transition and the diffusion capacitance. The diffusion capacitance is the forward capacitance, whereas the transition capacitance is the reverse capacitance. The capacitance in the reverse mode, reverse biasing, is the transition capacitance, whereas the capacitance in the forward biasing is known as the diffusion capacitance. So you can see this is the CD is the diffusion capacitance and CT is the transition capacitance. This is the equation of the transition capacitance. And in the later part of the discussion, I will tell you how does a diode act as a capacitor. See, if you try to recall the depletion region, the depletion region in between depletion region above side walls of the depletion region will have P type and one wall has the N type. These two walls are act as a plates of the capacitor and the depletion region act as a dielectric of the capacitor. Hence, the diode sometimes act as a capacitor. The capacitance is increased in the reverse bias and it decreased in the forward bias, but it exists in both the biasing, the forward biasing and the reverse biasing. This concept you will be clarified in later stages as well. And as you can see, this diagram, this is the diode. CT is the transition capacitance, and CD is the diffusion capacitance. Transition capacitance is due to the reverse bias, and whether CD is due to the forward bias. And this is the equivalent model of the diode with the capacitive effect. So, in practical sense, you have to consider both the resistance and the capacitive effect of the diode. So there is a diode specification sheet as well. So what are the factors? PD max, VD into ID, power dissipation, voltage into current, voltage across the diode and the current through the diode. And this is the power dissipation. This is the solar silicon planar structure of the diode. These things are important when you consider the manufacturing properties of the diode, how the diode is manufactured. You have to consider the voltage, temperature, power dissipation, maximum voltage, and maximum current. So when you work on a diode, just try to find out which kind of diode is that. Try to download the data sheet of that particular diode, and you can start working practically over that. Without the data sheet, you cannot take any decisions. So you can see with the forward voltage, reverse current, breakdown voltage, capacitance, reverse security time. All these parameters I have discussed, and these value are the minimum value, maximum value, unit, in which unit they voltage, microampere, nanoampere, volt, picofarad, microsecond. Now you have the what are the practical conditions, what are the test values, what are the practical values. So all these things comes under the data sheet, and at what temperature these characteristics are observed or obtained. So you have to consider all these things. So let me stop this video over here. And before stopping this video, just understood the notation of the semiconductor diode. This is the standard notation. This is P for P-type, N for N-type. Anode is positive, cathode is negative. This is a symbol. This is another symbol. This is another symbol. This is another type of diode. And this is another type of symbol notation. But generally, this black one notation is used. These are other industry standard, which are some for power diode or some other application. You can use these notations. You can see this particular notation. This is a general purpose diode. It looks like this. These two pins and the center button. This is surface mount high power pin diode. This is power stud diode. This is planar diode. This is beam LED beam lead pin diode. This is flat chip surface mount diode, power diode, and power disc puck diode. So these are different kinds of diode which you can see and in this particular book, and try to understand. Depends upon the application to application. And yes, in multimeter there is an option of the testing of the diode as well. So if you have the multimeter, you can test whether the diode is working or not. If it shows the beep sound is on, if it shows the hold value, then it is on. If it is a beep sound doesn't coming, it means there is a shortcoming in the diode. So you can test the diode with the multimeter as well, whether it is working or not. You can have this voltage ohm lead over here. This is the common point. This is the voltage lead. This is the common point. Connect that. If there is a beep sound come or the proper rating of the voltage is showing, then it means it is working. The cut-in voltage is there, then it means it is working. Otherwise, it is not working. So you can test the diode with the help of the multimeter as well, as you can show in this particular figure. And practically, when you will use a multimeter with a diode, then actual understanding you will come to know then only. But with this discussion, you will get the idea what I'm trying to say. Now, there are another instruments like curve tracer to test the diode and to test the characteristics of the diode, to draw the characteristics of the diode. This is known as the curve tracer. So if you want to generate the characteristics of the diode, just simply use a curve tracer from the Coetzee Agilent Technologies. And with that, you can trace the characteristic of the diode. Whereas in other topics, we will discuss. So let me stop over here. And the other topics we will discuss in our next videos. I hope you like the video. And if you have any comments or suggestions, and if you have any questions, just post them, and I'll be really happy to answer all your questions. Thanks for watching. Have a nice day.